Hello everyone, my name is Sagar Sajeev. I'm a master's student at University of California, Davis, and today I'll be talking about my work, regular expression processing on a many core platform. Firstly, we'll be going through the outline, where I'll be talking about the motivation behind the work, background on regular expressions, talk about our platform on which the framework is actually implemented on, how exactly the implementation actually works around, talk about the simulation and evaluation setup, including the comparative processors, talk about the key performance results, and summarize it with how exactly the combined performance, power, and area works out. So, firstly, as we know, regular expressions are heavily used in intrusion detection, bioinformatics, and log analysis, such critical fields. Now, these applications process large stream of data and need high throughput with low energy. Traditional CPUs and GPUs face a lot of memory and power bottlenecks because of their energy intensive applications, and that is where kilocore comes into picture. But before that, a little background on regular expressions. Regular expressions are used for searching, manipulating and matching text according to user's input. According to Friedel, regex patterns are actually built on meta characters and literals. Meta characters provide advanced matching capabilities, whereas literals provide, fixed textual content, such as a character or a set of words or strings. They are primarily implemented using finite state machines, which are also called as finite automatons, which can be deterministic or non-deterministic in nature. To talk about the kilocore platform on which we have built our regex framework is a 1,000 core platform built on 32 nanometer IBM fab based PDSoI CMOS tech. It has close to 621 million transistors. The important aspect is all of the cores that are part of kilocore are independently programmable and asynchronous in nature. They have their local instruction data as well as instruction memory as well as data memory. My apologies. It's really parallel and low power in nature, which gives makes it a really good platform for this streaming workload, such as regular expression. Now, the idea behind the framework was to come up with a system which can actually parse the regular expression patterns provided by a user and perform matching and searching capability on the kilocore platform over the user input data, which can be PDF, text, database, etc. To help us in that, we have a pattern code generation tool which converts the regex pattern into a chain of many core kernels with help of two set of Python scripts, which are used for lexical analysis, lexical parsing of the pattern itself into regex symbols, and the other one for kernel generation and intercore wiring, things like that. Regular expression symbols that are supported by the framework are 38 in total. They consist of symbols from various classes. An important aspect to know is that these symbols were actually chosen on the basis of contemporary regular expression standards based out of Java, POSIX, PCRE. The PCGT tool handles the C++ based kernel generation for kilocore along with the intercore communication wiring as well as the task configuration prior to the regex operation itself. How exactly are these regex symbols mapped onto the kilocore processors? A good example is given here where you have a 5 regex kernel setup. So the first chain that you see is the sequential non-cyclic regex processing chain. It's able to pass the input data as well as the control information across the processor cores. And parallelly, the input actually also goes into a line buffer core, which is able to get the information from the final, uh, you know, kernel or processing core of the regex processing system. It receives the match from this final core, and on base of the match, it's able to spit out the line that is associated with the match to the user. The idea behind selection of our benchmark regex pattern was to ensure that there is coverage of at least one meta character from each of the regular expression symbol standards, regular expression standards, pardon me, from POSIX, Java, or PCRE. As evident in the diagram itself, it covers a host of symbols starting out from your wild characters to lookarounds and a couple of complex operators such as conjunction and alternation, which I'll be talking. They were handcrafted. This particular pattern was handcrafted to ensure high stress to the kilocore as well as the comparative processors that we'll be talking about. But before that, the complex operators which I talked about, such as conjunction and alternation. So the conjunction operator is identified using the ampersand symbol within a grouping label. The idea is to find sub-patterns associated on the either side of the ampersand over an input line. And because of this reasoning, you have a complex layout where there is a fan out requirement of the input data as well as the control stream from the previous kernels into the pattern matching cores. And there is a merge core which actually performs state tracking of these matches that come together associated to a single input line. And once it's able to find the data, it's able to send this out to the streaming core, which in turn sends your input data and the control data to the next set of kernels that are part of the regex processing chain. Another complex operator is the alternation operation, where you have multiple set of sub patterns or substrings that you need to find in an input line. The advantage of this particular implementation is it is highly scalable in nature, where you can have multiple cores that can individually perform their own pattern matching in these kernels. And an example highly, very nicely indicates that FGH was the actual pattern that was required to be found out in the input line and is hit in the second core. And irrespective of the behavior of the earlier kernels in the same setup, uh, it's irrespective of the data stream and the control stream. It can actually pass down the data to the subsequent set of kernels for the regex processing. Hence, no synchronization or state tracking is actually required for this implementation. And finally, to talk about the implementation layout of the benchmark itself, it includes the conjunction as well as the alternation operators, which we talked earlier, along with multiple other host of regex symbols or classes in form of quantifiers and character classes, etc. Again, the setup remains the same, where you have the line buffer core and the final core, which is the range fixed core, is able to give information to the line buffer to provide the associated matches according to this benchmark. Um, through the simulation and the evaluation setup, we built 28 synthetic input files through random number generator. And each of these input files had input lines varying from 5 characters to sort of 200 characters, which is close to 3 to 4 lines of sentences in a normal text or a novel that you may read on a day-to-day basis. The data, the experiment was actually compared against Intel Core i9, AMD Ryzen 7, and an NVIDIA GeForce MX 150 chip. And the CPU profiling was done on grep, while the GPU profiling was actually done using the Rapid CODF package. We had to come up with our own Python script that performs the same functionality as of the benchmark, which we discussed earlier. And this particular script was actually run against the 28 input file. So all in all, the measurements for the data were actually taken for up to a total user input data of 1.5 to 1.6 GB across all the processors. Now, I'm happy to go through all of the performance results, but to cut it short, Kilocore performed thousands of times better than the commercial devices in throughput per area metric. And if we talk about energy efficiency, where we have to drive low amount of energy for such streaming workloads, Kilocore performed tens of thousands of times better in the energy efficiency sector. All the results were normalized to 32 nanometer CMOS for fair comparisons, and the scaling references are provided in my conference article. Finally, to talk about the combined, power performance area metric, the combined, value, Kilocore sits on top right of this plot, which indicates that it's able to give maximum throughput per area, and it's able to process, maximum amount of characters per unit energy in comparison to these metrics. So in short, Kilocore was able to perform the tasks in fewer resources per unit of useful work in comparison to all of the, comparative processes. With that, I would like to thank my advisor, Professor Bas, people associated to the VLSI Computation Lab, past and former students who were actually working on the UC Davis Kilocore project for the hardware platform and the infrastructure itself. And support is thoroughly acknowledged for AMD as well, who have been a supporter of all of the project ventures at PCL. Thank you very much for listening to my talk, and I'm willing to take any questions from the audience and the panel themselves. Thank you once again.